So thank you very much to Mike for introducing me. So the title of my talk is the F method for orthogonal and for spinors in general. And I will talk about the use or application of this method to orthogonal and symplectic spinors. So first of all, I should mention that the F method is one of the inventions by Toshi and some of his collaborators, and is, roughly speaking, the procedure which allows to pass from some algebraically defined problems to some analysis, based on a collection of partial differential operators. So the content of my talk is roughly can be divided into three parts. So the first part is to show you, based on the F method, the classification of equivariant differential operators on spinors in conformal geometry. The second part of my talk, and I will switch to the symplectic situation, and I will try to, and I will describe the realization of constant symplectic Dirac operator acting on symplectic spinors in projective geometry of dimension 2. And then I will try to generalize point 2 to arbitrary dimension in the following sense. So I will introduce the sort of series of equivariant differential operators, which are again based on the symplectic Dirac operator. And again, they will act on symplectic spinors, but not in projective geometry as in the point 2, but in contact projective geometry of arbitrary dimension. So that's the task, and all three cases will be described by introducing, the system of differential equations which define or which enter the machine of F method, and then they will be solved, and the corresponding equivariant differential operators will be presented in an explicit way. Okay, so I should say in the beginning that G equivariant differential operator, as is well known, and it's now this classical topic, which act on the principal series representations for a given group G, Lie group G, can be recognized in the study of homomorphisms between generalized Verma modules for the Lie algebra G. And they are determined by the image of the highest weight vectors. And such images are referred to as the single vectors and characterized as the vectors in the generalized Verma modules which are annihilated by the positive nil radical with U with respect to the chosen parabolic subalgebra P in the German G, in the Lie algebra G. And then the F method allows to find not only explicit or precise positions of single vectors, hence explicit formulas for G equivariant differential operators acting on a given representation space, but also, the complete classification of such possibilities for such single vectors. Okay, so the setup is quite similar to the notation which was introduced in the previous lecture. So the pair G and P is the real reductive Lie group and its parabolic subgroup P, and P has the Levy decomposition L times 2, where L is the Levy subgroup and U is the unipotent subgroup of the parabolic, and the round brackets containing R are the Lie algebras for G and P and L and U, and the complexifications are G, P, without any R, without any C. Complexified Lie algebras of G, P, Lu, and so on. Okay, so first of all, I will start by kind of some sort of, I will give you a description or kind of review what the F method is and which data are needed and how it works. So let V denotes a complex, simple, finite-dimensional L module extended to P module by U acting trivially, and V superscript star denotes the dual P module to V, and lambda, which is an element of P homomorphisms on the Lie algebra, but valued in the Lie algebra of the parabolic subalgebra P with values in C, defines a group character denoted by exponential of lambda of P. And we will also need that rho shift. So rho is that special element which is given by 1/2 of the trace of the adjoint action of element P acting or restricting to the positive numerical U of P. So this allows to define the notion of twisted P module depending on that continuous parameter on the character lambda, perhaps shifted by rho. And then the principal series representation of G on the vector space of smooth vector on the vector space of induced representation from P to G, and the P module V twisted by character lambda plus rho of smooth section of the homogeneous vector bundle over G over P associated to that inducing module. So this data allows to produce the infinitesimal action, which is a homomorphism from G to the tensor product, where the first factor in the tensor product is or denotes the complex algebra of smooth complex linear differential operators on the open Schubert cell UE, which is given by such P classes which come from the Lie group whose Lie algebra is the opposite radical to U. So it's denoted here is denoted by U bar. And this the action is such that it acts in the non-compact picture of the induced representation on the vector space of smooth function on the Schubert cell. Tensors with values in that vector inducing representation V, twisted by the character lambda plus rho. Okay, so the key ingredient here is the space of vector valued, so D prime is subscript O on the UE denotes the tensor with V is the space of vector valued or V value distributions on UE supported in the units on the P coset of the neutral element of the group G. So that's a point in G in the homogeneous space G over P, and this space of vector value distributions is module for the algebra, complex algebra of again this tensor product of the space of differential operators on UE times the space of linear maps of V's, in other words, endomorphisms of the volume. And this means that we obtain the action which is denoted by pi subscript lambda for an element of the Lie algebra on that space of distributions. Now, the exponential map identifies UE with the nilpotent Lie algebra U bar. That's again the opposite new radical to the chosen parabolic subalgebra of G, and we need to describe it in a convenient way, in a convenient form. So the notation A with subscript U bar denotes the viral algebra of the complex vectors or over the complex vector space U bar. So it can be shown. It's elementary show that to see that the vector space of distributions on U is supported at that P coset of the neutral element can be conveniently can be identified as module over AU bar as a module over that by the quotient of AU bar, by the left ideal generated by all polynomials on U bar vanishing at the origin. So that's what the identification is, and it's the map going from the corresponding tensor product, which is identified with the generalized Fermat module induced from the vector from the P module from that representation twisted by character to the right hand side. So first to the distributions, and then to the quotient regarded as module over the Weyl algebra over U bar is UG module isomorphism. Okay, now so another piece of notation is the collection of linear coordinate function on U bar with respect to the space of root spaces of U bar, and y1 up to yn is the collection of dual linear coordinates on the dual vector space U bar superscript star, which is identified by using Cartan of G with U itself. And then we can use, we can use algebraic Fourier transform, which allows to it's a map between the two algebras, A over the Weyl algebra over U bar and Weyl algebra over U bar star, identified with U itself. And this map is given just, it's induced on the generators of the algebra. So to xi maps to differentiation along the yi coordinate, and the differentiation in the xi coordinate goes to the variable, the dual variable yi, the dual coordinate. And this map gives the vector, induces the vector space isomorphism from it's a vector space isomorphism from the left-hand side to the right-hand side. And the right-hand side, when we quotient this Weyl algebra over U bar star with the Fourier dual of the corresponding left ideal, so can be identified with the polynomial algebra over U bar star. And the identification is clear, so this coset, I coset of an element Q goes to Fourier transform modulo the corresponding Fourier image of the ideal II. So we can compose the previous map denoted by phi with subscript lambda with tau, with isomorphism, or vector space isomorphism, to get another vector space isomorphism from the corresponding generalized Berman module to the polynomial algebra on U bar star valued in that representation. So notice that there is shift in the corresponding character, which is due to several conventions and due to the origin of the two maps. Okay, so the previous representation pi lambda can be Fourier transformed to the representation pi hat lambda. So again, it goes from G, it's a homomorphism from G to the Fourier dual Weyl algebra A over U bar star, again tensored with the endomorphism algebra of the inducing representation by character lambda plus rho, and this action is the action again on polynomials on the numerical radical O times that representation. So in some cases, typically in the third example, which I'll give you in the end of the talk, so we will need to employ the symmetric algebra isomorphism, so vector space isomorphism between symmetric algebra over U bar of the opposite numerical with the universal enveloping algebra of the opposite numerical. In the first two cases, when the corresponding numerical will be or is commutative, so the polynomial ring is isomorphic to the universal enveloping algebra on the corresponding nil radical for the parabolic decomposition. So here's the definition. So I think the definition is completely standard. So the algebraic problem we would like to solve or we would like to understand. So the definition says that when V is a complex, a simple finite dimensional L module extended to P module by U acting trivially, so then we define the L module, or we define the vector space of U invariance of the generalized Fermat module as the collection of such vectors which are annihilated by action from the left by all elements in the numerical, the positive numerical for the parabolic decomposition for the corresponding parabolic. And one can easily show that the space is L module, has a structure of L module. And we call term or denote this vector space as a space of highest weight or single vectors in this UG module. Now it's clear, so we will need to analyze or understand how this, the L module structure in an explicit form, explicit way when constructing equivalent differential operators. So it's, by Frobenius reciprocity, basically we get that home over L of a given P module, when restricted, that's L module, into the space of appearing in the previous definition, is in bijection with the space of Hom for GP homomorphisms for the two generalized Fermat modules, the first induced from W and the second induced from the P module V. Okay, so now the key object is the space, which is okay. So I will introduce this space. So now we would like to find all elements in the polynomial ring O times inducing representation. So that in the Fourier dual action, for all elements or all elements acting in a Fourier dual action with subscript lambda on such vectors is 0. So we denote or call this space or sort of solution space of the system of differential operators represented by the collection of P hat lambda x. So it's sufficient to take for all elements the root spaces contained, which generate the corresponding positive numerical. And the space is called solution space for the pair G and P and the corresponding vector valued polynomial ring, and that F just indicates that it's Fourier dual picture for that representation, because here is appearing the hat. So we are acting in Fourier dual situation. And again, it's elementary or easy or straightforward to show that the map tau composed with phi lambda induces the isomorphism between the space we would like to understand, so the space of U invariance in generalized Fermat modules of this form, with the corresponding solution space for the pair GP and the vector space described a while ago. Okay, so once again, so the action of such elements produces a system of partial differential equations for the elements which belongs to that space, and in preferred situation, I will show 3 examples which are based on spinors, both orthogonal and symplectic spinors. We will be able to completely classify all solutions in such cases and construct explicitly all solutions as elements in this vector space, and then translate them to elements of the corresponding generalized Fermat module. Okay, so in other words, we somewhat turned the problem of finding single vectors in the generalized Fermat modules into analytic problem of solving the system of partial differential equations. Okay, so here is the the content of this paragraph just says that mostly, for geometric analysis on manifolds, people are interested not just in single vectors or homomorphisms for generalized Fermat module, but rather in homomorphisms in the category of differential or G-equivalent differential operators acting between 2 induced representations. So in the end of each example, I will give you the explicit form of such equivalent differential operators. Okay, so here's the first example. So we will have 3 examples. So the first example is related to orthogonal spinors and the appearance and the role in conformal geometry. So the Fleck manifolds corresponding to the model of conformal geometry is usually or classically constructed out of the ambient space. In the signature, I also introduced the general signature. So we'll take the ambient space, the real vector space, Rp plus 1, Q plus 1, and then we consider the matrix of the scalar product on the vector space, and then in the coordinates with respect to a given basis, we consider all vectors which have 0 norm or 0 length with respect to the scalar product, and they form the cone, which is called null cone, and its projectivization is the model of conformal sphere, where this means that the conformal structure is induced on the quadric given by or denoted by SPQ. In other words, this quadric, the conformal sphere, is given by the quotient by the quotient G over P, where G is special orthogonal groups. That suggests just the component of identity of signature p+1, q+1 with real coefficients. And one can see that the stabilizer of one specific vector lying in that cone is or gives the corresponding parabolic in the form GL1R times. So that's the central element. So that's simple part of the Levy factor. That's SOPQR, and everything is semi-direct product with the vector group Rn. So that's isomorphic to the positive. The unipotent group of the positive numerical in the parabolic decomposition of G. Okay, so in the Dynkin diagram notation, so some people like to use kind of just combinatorial prescription for denoting or describing the corresponding generalized Fleck manifold. So the conformal geometry corresponds to kind of crossing the first simple node or first simple root in the B and D series of simple Wrigley algebras. And one additional remark says that because we will be working with spinors, so we will need not just the Lie group G, like a special orthogonal group, but we will need its double cover. Its double cover, and it's denoted by G tilde. In this case, it's spin, the connected component for identity of spin p+1, q+1 R, and the corresponding, denoting the corresponding covering homomorphism by psi. So P tilde denotes and is the parabolic, which is the pre-image of the parabolic subalgebra, subgroup which we discussed on the previous slide, and the Levy part, Levy component of the lifted parabolic P tilde is spin PQR, and in fact psi induces an isomorphism of generalized Fleck manifolds G tilde over P tilde with G over P. So that's another model of the conformal sphere. So now we would like to produce, in our first example, in the example of conformal geometry, how the F method works, and what is the system of partial differential equation which leads to single vectors defining or classifying equivariant differential operators on spinors in conformal geometry. So, our inducing representation in this case will be spinor representation, again twisted by character lambda, perhaps lambda plus 0 when rho is, again, that's the special character, that rho shape. And then we have to introduce the collection of coordinates. So again, with respect to the root spaces, we denote x1 hat up to xn hat, the linear coordinate functions on U bar, on the dual of numerical corresponding to the choice of parabolic, and by x1 up to xn, the dual linear coordinate functions on U bar star. And we have to introduce, or we introduce the two while algebras on U bar and U bar star. So they are generated by coordinates plus the differentiation in coordinate directions. And so what's important on this page is that we also use the notation for Euler homogeneity operators, just for variable x and variable x hat. So after some tedious calculation, we are able to produce the explicit formulas for the action of particular root spaces in the representation pi lambda and pi lambda hat. So as for the elements of the negative nilradical, so the corresponding generators act in the representation pi lambda by first of the differential operators, as all elements do. And in the Fourier dual picture, the elements from the negative nilradical act by multiplying by the corresponding coordinate function. So similar situation happens with the elements which generate the Levy factor, So H denotes the elements which generate the centrum, and HA describes collectively all elements which generate a simple part, simple component of the Levy factor, which is, again, SO. In its complexification, that's SO and C. And so again, the two or collection of differential or first order differential operators, while in the Fourier dual, not while, but in the Fourier dual picture, the Fourier dual representation, again, we get first order differential operators. So A is just the notation for the matrix, which is in the simple part of the Levy factor. So for the matrix belonging to SON. And the most important component of that, of the collection of root vectors from G are the root vectors from the positive radical divided by U. So we have n of them and a couple of them. So in the representation pi lambda, they act by first order differential operators. And the coefficients are in the corresponding coordinate functions quadratic, while in the Fourier dual picture, such elements act by second order differential operators, and the corresponding coefficients are linear in the Fourier dual variables x1 up to xn. So this collection, forms the system of differential operator which enters the F method, and we have to find the solution space of all of them when acting on the space of polynomials on U bar star tensored with representation of our interest, which will be the spinor representation. Okay, so I think many of you know what the spinor representation is. So once, again, working in a complexified picture, so simple part of the Levy factor is isomorphic, factor is isomorphic to SO and C. When n is even, the spinor representation is, or splits into two irreducible components. There are two of them, while for n odd, there is just one simple spinor module. And the generators of the Levy factor, or the simple part of the Levy factor, act through the endomorphism algebra of the spinor representation, which is so-called Clifford algebra. So the corresponding homomorphism from SON to the Levy algebra is given by the following formula. And I think it's not necessary to describe a Clifford algebra to give many details to Clifford algebra, but it can be, or it is constructed or is defined as a quotient of the tensor algebra on the numerical isomorphic to Cn by the relation which is non-homogeneous. So on the left-hand side, we have elements of degree 2, while on the right-hand side, the one is the generator of the field of complex numbers, which is in the 0 degree part of the tensor algebra TCN. Okay, so this will not be needed, and this is something we should need. So again, when we forget the initial representation pi lambda and specialize to the spinor representation twisted by character lambda plus rho, so this is how elements of the negative numerical do act in this representation. This is how the elements from the zero graded parts of the parabolic decomposition of G do act, and we are mostly, we are interested in the action of all elements from or generators of the positive numerical, and the action in that Fourier dual representation pi hat lambda. And this is more invariant notation based on the use of the Dirac operator on Cn or on U. And here is the homogeneity Euler operator, and here is again the action of Dirac operator. So EI is the notation for the basis of Cn, which is identified, which is isomorphic to the positive numerical u, and it acts through the Clifford algebra as a vector on spinors just algebraically, while the previously mentioned, module structure of on spinors over the Clifford algebra. Okay, so what we will need? So. Okay, so I will skip. I will return back to our space of interest. So it is difficult to work directly with the collection, with the n tuple of operators, which was mentioned a while ago. So it's better to take a linear combination of them. So instead of taking pi lambda head G1, pi lambda head G2, and so on, so it's convenient to introduce the three operators P1, P2, and P3. So when we contract the corresponding index, so either by EJ, regarded as acting by a Clifford algebra action on spinors, or by XJ, or by up to corresponding epsilon j, differentiation in the direction of jth coordinate. So the three operators P1, P2, and P3 have a very convenient form. So they are just written in terms of D, X, and EX. So here is, sorry, I have to come back. So this is what D is, so that's the formula for the Dirac operator. E is that homogeneity operator, which acts as identity on values on the spinor module, and that's X, that's kind of Fourier dual of D. So X is linear function, EJ is again acting via embedding into Clifford algebra on the spinor module algebraically. So the claim is that these three operators, which are just expressed in terms of E, X, and D, the solution space or the common kernel is the same as the common kernel of the collection of n tuple of operators in the Fourier picture. So P hat lambda G1, P hat lambda G2, and so on. One implication is trivial. In the second implication, one has to work a bit, but can be proved quite easily. So once we have this, that the system of now three operators entering the F method, we have to adopt or adjust a little bit the vector space on which these three operators will be acting. So we'll return back to our polynomial algebra tensored with the spinor representation. And it's a matter, or it follows basically from the whole duality for the pair of special orthogonal group and the superly algebra OSP12, which is generated by three operators D, E, and X, that these three operators, that OSP12C, is the centralizer of the action of SON on the corresponding vector space. Consequently, this vector space can be decomposed as direct sum of simple modules, which are of the form x to the power of b times MA, where MA are is the space of spinor-valued polynomials which are in the kernel of the Dirac operator. So they are called monogenics, similar to harmonic polynomials for polynomials without the value in spinors. And A just means their homogeneity. So A, B are two natural numbers including 0. So now we see that everything is expressed in terms of D, X, and E, both the domain on which we act by the corresponding three operators P1, P2, and P3. So by the way, this is the scheme of the decomposition. So the three operators X, D, and E act horizontally. So the corresponding horizontal lines are modulo for the dual algebra OSP12, and each column is the SONC decomposition of the space of polynomials of given degree or fixed degree, valued in spinors. So now we can solve, and this reformulation leads immediately to the solution space. It isn't easy to find what the solution space is. So the claim is that in the odd case, when n is odd, in the sense that when n is even, so there is analogous classification result, which is not so easy to write, which is more complicated to write it explicitly because the spinors split into positive and negative spinors. There are two simple components, two simple representations. But in the case of when the dimension of the corresponding manifold is odd, or the dimension of the numerical is odd. So the space of interest has then three type of solutions. So if lambda is sufficiently non-integral, then it contains only M0, and M0 is the space of spinors, and it corresponds when we dualize to equivalent differential operators, which will be identity on the corresponding when acting on the corresponding vector bundle induced from spinors. When lambda starts to be sort of integral in the sense that lambda minus 1/2 is natural number, so the solution space contains M0, I mean the copy of spinors, and one of the modules which are in the kernel of D. So that was one of the modules lying on the diagonal in the previous graphical picture decomposition of spinor-valued polynomials. And if lambda plus n½ minus 1/2 is a natural number, then the space of solutions contains M0, and M0 shifted by power of x. So x was that injective operator acting horizontally, sort of dual to the action of Dirac operator when acting on spinor-valued polynomials. So this is the way how the corresponding L modules are embedded inside the space of U invariants and the generalized Berman module induced from spinor representation twisted by character lambda. And so when dualized to equivariant differential operator, the classification says, so the first part of the theorem just describes only the corresponding geometry. So what is the group G tilde and P tilde that was mentioned on previous slides. So I will directly skip to the classification result. So first of all, there are equivariant differential operators which are called conformal powers of the Dirac operator. So this is what they are. They corresponding to I mean, in the non-compact picture of inducing representation, they act on spinors twisted by certain character, which is specified by the value of by one of the numbers which was mentioned in the previous classification scheme for the single vectors. And here is the equivariance property when acting on induced representation, induced from spinors twisted by certain character, and that's the explicit value of the character. Okay, and there is another collection which comes from the second row. So collections coming from L modules realized by kernel of D. So then we have another collection of G equivalent, G tilde equivalent differential operators on spinors, but the values are in more complicated representations, which live in the tensor product of spinors and symmetric powers of fundamental vector representation, and these operators are called conformal twistor operators acting on spinors. Okay, so that's all related to the first example. So another example I will discuss is the case of so-called symplectic Dirac operator acting on symplectic spinors and its realization in projective geometry of dimension 2. So probably I should mention that this geometry, I will describe it immediately. So in the Dynkin cross diagram notation, so the first example corresponds to this case or the B series. So the second example corresponds to this case, and the third example will correspond to this homogeneous space, to this generalized flat manifold. So okay, so the second example, which corresponds to projective geometry in dimension 2, probably I should say in the beginning that the symplectic Dirac operator was introduced by Constant many years ago. It was introduced as an operator acting on symplectic spinors, and by that we mean the two simple modules of the symplectic module called Segala-Shelby representation. So that the symplectic operators acting on symplectic spinor in real dimension 2. So we will realize the corresponding symplectic operator in this geometry, in projective geometry of real dimension 2. So we will, using F method, we will prove that this operator is an equivariant differential operator acting on the SL3R, and there is tilde. So we have to use, again, as we did in the case of conformal geometry, we have to pass to double cover of special orthogonal group to the spin group. So here we have to pass to double cover of SL3R. So that principal series representation induced from the metaplectic representation to simple modules of the metaplectic or Segala-Shelby representations or metaplectic representation of SL tilde to R, and it's twisted by certain value of central element for the parabolic, which I will describe in a moment. So probably I should mention that the importance of this operator is that its solution space, say on the symplectic space R2, can be constructed explicitly, and it's a consequence of the metaplectic whole duality for the pair of Lie algebras. So MP2R is a metaplectic Lie algebra of rank 1 and SL2R. And the underlying Harish-Chandra module of the solution space of this operator for the Harish-Chandra pair SL3R and SU2 is one important representation. It's a unitarizable, irreducible representation, which is equivalent to the exceptional representation of SL3R tilde. So this representation was studied in the past by Torasso, for example, also Ben Erstedt. I mean, realized the symplectic Dirac operator. He brought the realization by Steinway's gradient in projective geometry of real dimension 2. So this, novelty of this approach is that, after some technical modification, because we have to deal with infinite dimensional representations as inducing representations, the F method can be adopted to these cases, and I will show you the corresponding system of differential equations, which are of a higher, not of second order, but of a higher order in this case, which then lead to or construct as a single vector, produce a single vector, which then corresponds to the symplectic, to the realization of symplectic Dirac operator on the two-dimensional sphere, which is in the sense of topological spaces, double cover of real projective space of dimension 2, right? It's non-orientable, so we have to do double left of that to two-dimensional sphere, which is not only orientable, but it's symplectic manifold, and so it makes sense to introduce to deal with symplectic Dirac operator on this Fleck manifold. Okay, so here are some comments related to some technicalities which one encounters when dealing with a problem, when inducing with infinite dimensional representation. So, for example, when taking infinite dimensional simple R module and trying to produce type of module which is kind of generalization of generalized Verma module. So in fact, this is not an object of the parabolic BGG category OP because of the lack of L finiteness condition and so on and so on. But despite of all these facts, all these technical problems, the F method can be adopted to such situations and can be used and applied to the cases as the point 2 and point 3, as the example 2 and example 3 in my talk. So again, as it was before, so the corresponding, do I have something more? I don't. So the corresponding parabolic subalgebra is one-graded, which means that the numerical is commutative and it is of real dimension 2. So with respect to the root spaces in the opposite numerical, we have to introduce two coordinates, say x and y, and the dual coordinates on u bar star, again denoted by by, well, on the U bar star they are noted by x, y, and the corresponding differentials in the coordinate direction, while on the U bar they are denoted by x hat, y hat, and the corresponding differentiations in coordinate directions. Here is the explicit realization of the inducing representation. So as I said a while ago, it's given by two simple metaplectic submodules of the Segala-Shelby representation. So that the Fock model are given by unitarizable MP2C module, which is isomorphic to the polynomial algebra in one variable, which is denoted conveniently by Q, and the corresponding generators act by well-known or notoriously well-known formula. So second derivation in that fiber direction, the direction of the representation, and Q square, and the shifted homogeneity operator. Okay, again, after some effort, we can produce the corresponding representation, representation pi lambda and representation pi lambda hat in the Fourier image. So we will not be interested in the action of the elements of negative numerical. We will not be interested very much in the action of elements of the corresponding Levy factor, but we will be interested in the action of elements of the positive numerical. So there are two of them. They are denoted by E1 and E2. So pi lambda in the initial representation, these two root vectors act in the following way. So as we can see, so they are differential operators of second order, and that's because in that fiber variable we differentiate in the variable Q, so that's in the vertical direction, in the direction of the inducing representation. So when we produce the Fourier dual picture, so that's again pi lambda hat for a given for arbitrary lambda. So the two root spaces, the two generators of the positive numerical act by these two operators, and as we see, so these operators are of third order. That's because again in the direction of the representation, we have to use kind of differentiation with respect to the variable Q, so that operator, the two operators are of third order. So again, these two operators enter the F method, and we have to find the solution space of these two operators when acting on the ring of three variables, X, Y, and Q. And of course, one can rewrite these two operators in a more convenient form. For example, we see that the x dx and y dy is the total homogeneity in the variables x and y. And for example, this object is just the local notation in the variables x, y, and q of the formula for the symplectic Dirac operator. Okay, so again, when using Howe duality, when acting on the polynomial ring in two variables O times the polynomial ring in one variable, so altogether polynomial ring of three variables, which is in this case given by the pair of metaplectic Lie algebra, and its dual pair is the Lie algebra SL2, which is generated by, I will return back, so which is generated by, well, it's not here, so we will see it in the next example. So which is generated by D, the Dirac operator. It's a Fourier dual object, so that's XS, and the homogeneity operator in the base variables X and Y. So the claim is that the solution space in this case for the pair when G is SL3R and P is the corresponding parabolic and so on and so forth. There is only one solution when lambda is equal to 3/4, and that solution is spanned by L submodule of the corresponding space, given by acting by the operator XS on the Segala-Shelby representation. when x's is again, as I said, kind of Fourier dual with respect to variables x and y of the local formula in all variables for the symplectic Dirac operator. And so here is a situation when you dualize to equivariant differential operators, and that's, as I said, I mean, that's the fact that such operator exists in projective geometry of real dimension 2 was observed before, for example, by Ben Ørsted. So here is what G tilde is, what P tilde is. The corresponding homogeneous space is the double cover of real projective space of real dimension 2, so it's two-dimensional sphere. And the corresponding formula for ds has the formula which is well known if you open the old article by Constant on symplectic Dirac operator, and it's important that acting on certain weighted and Segel-Schiavale representation. So here is the intertwining property for the realization of symplectic Dirac operator in the projective real geometry of dimension 2. Okay, now the question, this is the last example. I have 10 minutes, which is fine, because I will not tell the kind of the detailed description in this case. I will explain, because it's this case, the situation is more complicated than the previous two cases. So I will talk about something which can be called contact Dirac operator acting on symplectic spinors in contact projective geometry. So this geometry is based, or the corresponding generalized Fleck manifold. This is the, Frost notation for the Dynkin diagram. That's how it's defined. So geometrically, the generalized Fleck manifold that's describing or introducing so-called contact or flat model of the contact projective structure is the homogeneous space G over P, which is again isomorphic to odd dimensional real projective space. And the group of symplectic automorphism of the vector space R2n plus 2, so this is G, acts, it's written here, so acts transitively on the space of lines in the vector space R2n plus 1 by the standard vector action. And the stabilizer of line is a parabolic subgroup, which is conjugated standard parabolic subgroup. And again, it's a Levy, simple part of the Levy factor is sp2 and r, and that's one central element, and that's the corresponding exponentiation of Heisenberg algebra. That's the Heisenberg group of dimension 2n plus 1. So this is what G and P are. And again, this picture is over here on the green board. And again, we have to produce our system of differential operator, which enters the machine of F method and which allows to find all single vectors in corresponding generalized Verma type module, and then which translates by duality to equivariant collection of equivariant differential operators acting on symplectic spinors. So the situation is quite similar to the previous one, to the second example. So we have n tuple of coordinates. So in both pictures, so for u bar and u bar star, we have n tuple of coordinates coming from one Lagrangian subspace, another n tuple coming from the other Lagrangian subspace of the first graded component of the Heisenberg algebra, and then we have that central element, so z commute that corresponds to that contact direction. So perhaps I should say that this geometry, the contact projective geometry, is the geometry which is foliated by symplectic leaves. So one can somewhat conjecture that something like that constant Dirac operator acting on symplectic spinor should appear when trying to construct equivariant differential operators acting on symplectic spinor in this geometry. So that's true. So we have the corresponding generators of one Weyl algebra the other Weyl algebra. So it's n tuple of coordinates from one Lagrangian, from the other Lagrangian, the coordinates corresponding to that central element of the Lie algebra. And similarly in the Fourier dual picture. And here is the notation. So we have to introduce explicit because we would like to have some explicit formula. So in that local chart coming from the exponential of the tangent space, or in other words, the opposite and radical, we can write the formulas for ds or define what ds is, E is. It's just, again, some sort of homogeneous operator in base variables x and y, and not including z, and that's kind of Fourier dual of ds, which is xs, and again, it can be thought of as a polynomial of degree 1 in variables x and y with values in endomorphisms of Segal-Shelby representation of symplectic spinors. And after some effort, so I mean it's straightforward but tedious computation to derive the following formula. So again what? So I will give you just the formulas for the Fourier dual of the action of particle root vectors in that in the decomposition of the Lie algebra G. So we will not be very much interested in the action of elements of root vectors living in the negative null radical for the corresponding parabolic. We will not be interested very much in the action of elements coming from the Levy factor, Levy part, and that's central element for the parabolic decomposition. But we will be again interested in the action of, in the Fourier dual picture, of the root vectors which generate the positive null radical. And so here is the formula, and because ds itself is a second order operator when counting both horizontal and vertical direction. So this is fourth order operator. That's corresponding to the highest root, and similarly for di and ei, generating the corresponding Heisenberg Lie algebra. So again, this collection, this 2n plus 1 tuple, enters the machine of Fourier method, that F method. And again, we would like to find its solution, the full solution space, on the space of polynomials on the null radical all times that Segal-Shelby, that metaplectic representation for symplectic spinors. And I will not give you explicit formulas for single vectors. Here is just translation to equivalent differential operators because perhaps they are more important in the end. So again, we have a collection of operators which might be called contact powers of a contact symplectic Dirac operator, whatever it means. I will give you the formulas on the last slide. And these are operators acting on symplectic spinors, on that Segal-Shelby representation. And again, after some character shift, they again land in the same representation. Here is the intertwining property. So that's one collection. So they are numbered by natural numbers. There is another collection of them. So they might be called sort of twistor operators, or acting on symplectic spinors realized in contact projective geometry. So they start, the domain is a space of symplectic spinors, and the target for such operator is just kind of more complicated representation, one of the representations which are in the which come from the tensor product of Segal-Shelby with symmetric powers of the fundamental vector representation of symplectic Lie group, of symplectic Lie algebra. So this is what they are. So now I will give you the explicit formula for the operators dA, we are going to it soon, just 1 minute. And okay, so here is the collection. So here are explicit formulas for D1, D2, D3, and D4. And you see that there is a general pattern. So there is kind of, these operators come in the factorized form. And there are some specific numbers which are squares of integers appearing in such units or bit in which these operators can be expressed. So again, ds is the formula for the simplex Dirac operator in the local coordinate chart, and xs is its redual in the base variables x and y, and we can give a general formula for any dA or dn, or d probably a, where a is any natural number. And what is somewhat remarkable on this is that the operator D1, when you look at its solution space, so the solution space is the highest weight module, it's irreducible, and has the same infinite character as the negotiable representation. So in other words, the kernel of D1 realizes the minimal representation for the symplectic or metaplectic group in this case, and this means that this representation, this subspace, is unitarizable. So in the same sense as Toshi, together with Band in the series of articles many years ago, constructed the scalar product on the solution space of Yamabe operator in the conformal geometry, is desirable to construct the corresponding unitary structural scalar product on the solution space of this operator. I don't know, I mean, in a geometric way, not algebraic way, but geometrically. So this is probably the next page. So to Toshi, happy birthday, Toshi, and many, many mathematically productive years. Thank you very much.